In this video, I'll give a brief introduction of mathematical induction. When we're doing a mathematical induction problem, first we have to define the expression in this step. And then we can move on to the base case, where we prove that at least one value works for the expression. And most of the time, we will use the most simplest case, and that's n equals 1. So proof n equals 1 is true for that expression. And then we move on to the induction step. And there are two parts in the induction step. The first part is we assume that n equals to k. And in the second part, we prove that n equals k plus 1 is true. And in a conclusion, we say that P1 is true because P1 is true, PK is true, and PK plus 1 is true. Therefore, by mathematical induction, Pn is true for all n values which belongs to a constraint by the question, and that depends on different types of mathematical induction questions. So we can think of the mathematical induction as like the domino effect. So in the base case, we're saying that at least one domino will fall. And in the induction step, we are first assuming that at least at any arbitrary domino will fall, and we are proving that the neighboring domino will fall, and that's true. So what we're saying is if any domino falls, then the neighboring domino will fall, and the neighboring domino falls, and the next one falls, and eventually all domino falls. So that's the basis of mathematical induction. And here is a general format for doing mathematical induction problems. So first we define Pn equals to the expression, and then we show true for P1. So the left-hand side equals the right-hand side. So because left-hand side equals right-hand side, therefore P1 is true. And then we assume that Pk is true, and we write down that expression, and K belongs to whatever constraints that equation, that problem has. And then we prove Pk plus 1 is true. Left-hand side will equal to right-hand side, and therefore Pk plus 1 is true. And lastly, because P1 is true, Pk is true, and Pk plus 1 is true, then by mathematical induction, Pn is true for all n which belongs to that constraint set by the problem. So here is a past paper problem from the IB mathematical examination. And it's a mathematical induction problem related to summations. So I'm going to use the same format I've talked about above to do this problem. So first, Pn equals to this expression. I just copied everything and say that Pn equals to this. And then we show true for P1. For the left-hand side equals to 2, right-hand side equals to 2. Therefore, because left-hand side equals right-hand side, therefore P1 is true. And then we assume Pk is true. And what we're doing is saying that we're changing all the n values from this expression to k. So all the n's here will becomes k. All the n here becomes k. Okay? And k belongs to all positive integers in this problem. And because this is a summation problem, Pk also equals to this expression. And this is equivalent with this expression. This is just an expanded version of the above. And Here comes the most difficult part. Prove pk plus 1 is true. So one very common technique we have to use here is substitution of what we have assumed into pk plus 1 to get the answer. So I will advise you to do the easier part first. And there's the left-hand side, right-hand side. And in this case, the easier part is the right-hand side because it's only this expression. This is pk, this is pk plus 1. Therefore, k becomes k plus 1 here. K become k plus 1 here. Done. And in the left-hand side, we have to use the substitution technique. So because pk equals to this expression, pk plus 1 is essentially, I'll write it out here, from 1 to k, r plus 1 times 2 to the power of r minus 1, plus this value, but all the k will be k plus 1. So k plus 1 is k plus 2, 2 to the power of k plus 1 minus 1, so that's just k. And this expression equates this one. So I'll cross it out. And this is the most difficult part. If we get this part done, everything below would just be algebraic manipulation. And all we have to do is we have to equate the left-hand side with the right-hand side and we'll be done. And what's happening here is we've showed that pk here plus the last expression here with k plus 1 instead of k. So this whole chunk represents pk plus 1. So we can write this expression as k times 2k because we have assumed above this expression equates each other. So this equals this. And below, move on to, we take the common factor of 2k. So k plus 2 would be 2k plus 2. And then we take the common factor of 2. So inside would become k plus 1. And here, you see that we're getting very close to the right-hand side. And what we need to do is to change this expression to 2 to the power of k plus 1. And we've finished the problem. We have proved that the left-hand side equals right-hand side. And we've proved because left-hand side equals right-hand side. Therefore, pk plus 1 is true. And then we move on to the conclusion step. Because p1 is true, pk is true, and pk plus 1 is true, then by mathematical induction, Pn is true for all n values which belongs to all positive integers.